So hello everyone. I hope you are doing good. Let me check if the yeah. So well, it's been a long break, and I wish that things wouldn't have come down to doing such kind of lectures, talking to a computer. But I mean, there's no choice. So we'll come back to the lecture series. I think by this point, you must have. I think Chir is almost done with his lectures. I think this few coming up this week. But the idea is this: I'll send you three 1 hour lectures, as I wrote in the email, about an hour each, and I'll be following the notes that I've given out on algorithms. So, well, I mean, not just any algorithm. I'm talking about something very specific. I'll come to that. But of course, algorithms for so these are like kind of what I call solvers for computing minimizers of convex problems, convex programs. But I mean, this is a very big literature. In fact, you can get a full textbook on algorithms. There is a textbook by Brett on convex optimization algorithms. It's a very big topic. We are just skimming the surface. In fact, we are not just doing that. We look at something that's quite quite fashionable in some sense. This has been a very active research area for the last at least for the last decade or so. I mean, anything more. So these are what I call first order methods. First order methods. First. So for this part, a good reference is Nesterov's textbook on convex optimization, right? Basically, I think it's one of the recommended references for this course. Uh, you can get it online. The PDF is, I think, it's freely available, and yeah. So you won't get anything in Boyd. There's absolutely nothing in Boyd that. Of course, Boyd does have a section on interior point methods and other things, uh, but there's absolutely nothing on this topic. Which I'm typically, in fact, you don't have many textbooks. You can have. There are surveys, tutorials, but I think the closest that anything comes to is Nesterov's textbook for this part. In fact, his name does come up prominently in this field. Is the kind of inventor of co-inventor of some of the very some of the stuff that is used in first order methods. He has this kind of a variant of a fast algorithm for finding something. It's probably the tightest and the fastest that you can get. I mean, okay. So we don't wish to do a lot. I mean, we don't do exhaustively cover every first order method. We just skim the topics and look at the main. The focus of this part of the lectures is to look at the main principles, not just for the designing the algorithms, but also for analyzing them. Right? We have already seen PS6. There's quite a heavy math coming in. Why you want inequalities, right? This is like kind of hard analysis in some sense, where you need very quantitative bounds and inequalities to understand what you call convergence rates or even convergence as such, right? So, for example, we will look at rates. We'll prove some rates, but in general, I'll kind of convince you that. If you have a convex problem and if someone tells you that can you solve it, let's say someone tells you I have a convex problem, I have a convex optimization and look, can I do that in MATLAB, right? It's a generic question. Look, I have a convex problem and can I do that in MATLAB? I mean, you don't have a very, it's too general a statement, right? Convex problems. I mean, what kind of convex problem, right? Unless you tell me a little more of the structure of the problem, it's quite difficult to say. In fact, let me go on record to tell you that there are convex optimization problems which surprisingly are NP hard. Let me repeat. So there. So for example, you know what's a convex program, right? So you have right. So C is a convex set. I'm working in Rn. C is a subset of convex subset of Rn, and F is a convex function, right? So there are, you can pick C and F. If I'm correct, it's C is Rn. In that case, it's unconstrained optimization. I'm not very sure, or maybe I'm not very sure. But let's say there are, I mean, or rather, there is a choice of C and F for which, you know, solving this problem, whatever it means, right? So when you have a computation, you know, you actually require, you know, definition of what computing means at all, right? So for example, you want to understand complexity, you have to first tell me what you mean by computation at all, right? So so let's say loosely speaking, there exists choice of F and C for which this problem is hard, it's difficult. There are no efficient algorithms at all. I mean, it's in fact provably NP hard. There are problems where you can, you know, reduce it to one of these so-called tough problems that people have, this list of tough problems. So it's as hard as one of those problems that are known to be sort of, that have been catalogued. So, but if I, maybe I'll make a clarification here for those of you who have studied algorithms and complexity theory. Just be a little careful with optimization problem. You see, it is non-trivial actually to sort of think of, you know, let's give it some, let's say it's a solvable problem. Let's say F star, even forget solvability. Let's say F star is the minimizer, right? So F star is not minus infinity. F star is a finite number, and I'm asking you to tell me, look, I give you C and I give you F. Can you compute F star for me, right? You see, there are almost everything that I say has a challenge. It comes with a challenge. The first thing is, what do you mean by C? You know, so how do you describe C to a computer? It's like it's part of your parameter. You know, it's part of your data. So you have to encode C, encode F, right? Using bits, you have to encode F and C, right? Well, I mean, MATLAB does it, right? I mean, it can do. You can solve a lot of convex problems, so it can be done. But the important point is, well, up to that encoding business, at least tell me what do you mean by, you know, so you have F star, it's a number. So within a classical, you know, theory of computations, right? How do you see this as a decision problem, right? You know, typically the problems that you solve are decision problems, right? And the question of, you know, how quickly can you say it's a yes or no, right? Or how efficiently. So how is this a binary or a decision problem, right? That's not entirely obvious, right? But I'll not get into you know, the details of that. But just let me tell you, because, well, I mean, people have a way of proving hardness. You see, if you want to show something is hard, let's say, not easy, hard, then you see, you can always ask a question like this. Does there exist some x in C for which fx is less than or greater than some number? Okay. So now I'm giving you three inputs, C, F, and a number. It could be F star. And I'm asking you a question, does there exist an x in C such that fx is strictly less than F star, right? So you see, that's like in some sense the most basic question that you can ask, because what you're doing is you're trying to ratify whether this statement is true or not. You're trying to decide whether this F star that I have offered you, let's say it's 1, is 1 the minimum of this problem or not. And you see, in some sense, if you can't even check, right? If you can't even check that 1 is a minimum, there's no chance that you'll be able to solve it. So, now if you go back to the definition of mean, it means that if F star is the minimum, it basically means, what does it mean? The two ways of saying, well, I mean, the straightforward way is by definition for all x in C, fx is greater than or equal to f star, right? But you know that that's just one part of the statement. It means that f star is just a lower bound, and you know that this is an inf, right? This is an inf really, so you have to actually show that this is also tight, right? You can get very close to it. But up to that technicality, you see, this is a very valid question that you can ask. So, for example, if this is true, then f star, right? F star, you know, is a sort of candidate for being a minimizer. However, if you find an x in C for which fx is strictly less than, that means this is false, right? See, checking this is again very difficult. So for all x, you have to check that. However, if you can do something simpler, you just out of some guessing or whatever, you pick an x in C for which fx is strictly less than f star, then you can reject that proposal for f star. You can say that no, that f star cannot be a minimizer, right? Because I already know there is a guy who's taking values less than that, so that's out. And then you see what's next in line. If you can answer such questions, whether it's less or greater, then you can do a kind of a binary kind of search in some sense, right? You can split the technicalities. You can take values in the real lines. What do you mean by splitting the real line? Well, let's say roughly, if you think of the problem at this takes values in a sort of a bounded interval, you can start chopping the interval, and then you can keep asking questions on the left or right of the interval, right, the minimum, and you can keep narrowing down, and that's the details of how you do. But please remember, when you're talking about computations and complexity of solving problems and all that, so basically you have at the back of your mind some kind of a decision version of the optimization problem that you're looking at. Right? Per se, it's not a decision problem, but you can actually sort of reduce it to kind of decision problems. With that, I'll not get into the details of this anymore, and let us look at more like heuristics or algorithms for solving such problems where f and c have certain structures, specific structures, right? Apart from being convex. So as I said, just let me, I think I didn't say the main thing. So just to finish those comments, so within that, notion of whatever, decidability and all that, there are problems, choice of f and c, for which, finding f star is NP hard. That's what I wanted to say. So, having said that, you see, so this, I mean, generally, if you have f and c, and if you ask for a solver, you cannot get one, right? But in practice, we usually have very, very structured problems. For example, C is often the whole Rn, or your real line, right? There's no constraints at all, and f is some nice function, possibly differentiable, and you use gradient descent, for example, right? So if I just do a little fast forward, let's go a little fast forward. Most of you know about gradient descent, right? So you see, even with very accepted notions of algorithms and all that, proving things, showing that they do work across all problems in the worst case sense is tricky. So for example, consider C to be, right, C the whole Rn, right, and that's the bare minimum you need to solve. Of course, the standing assumption is that f and c are convex always. I'm not writing it every time, but on top of that, assume that this is unconstrained and f is differentiable. That's the bare minimum you need, because in this case you can define a gradient and hope to move against the gradient, right? So uh, uh, right? That's the gradient method, right? You start from some x naught and you keep iterating, right? So you try to refine your estimates every time with the hope that what hope? That's the tricky part. So already I can ask you certain questions which either you might not have thought about before or you might have thought about and not have found the solution. Is this. So you're generating a sequence, right? It's a sequence of vectors in Rn, right? So right. So sometimes in short, right, so I'll use this shorthand sometimes, just xk possibly sometimes. To me, not just xk for some particular k, but the whole sequence that's generated by this recipe. So you see, the seed that you need is x naught. Once you fix x naught, this is a totally deterministic sequence, right? So you know x1 gives you x2 and all that. So starting with x naught, you can think it of a pair. You give x naught and an algorithm, this gradient descent, and the whole sequence is determined, right? So so what happened? Sorry. Sequence in R. What does the, what comes to your mind immediately is, you have a sequence, things moving around. The very first thing that would come to your mind is, does this converge or not? Does this stabilize at all? Eventually, does it lock onto something? So, answer a question. What's the natural question? I hope you can see the board. Pull it up a little. What's the natural question? Does this sequence converge? What? So basically you have to analyze the convergence of this sequence, right? So what do you have in your hand? You know that f is convex, f is differentiable, and that is it pretty much, right? Convex differentiable function. Just notice something. There is a step size, right? I didn't say. So for example, morally speaking, this can also be a function of this called variable step size. But I don't want to make things complicated. Let's say fixed step size. It's called a step size, right? Let me use a fixed step size. By the way, I'll come back to that and write out everything properly, possibly in the next lecture. I'm just trying to motivate the topic. So, well, you can use this, and there's something called backtracking line search where you actually fix this age at every iteration based on some guarantees, and sometimes it works, sometimes it doesn't, right? You can generally do sort of some kind of backtracking to fix this age. The whole principle is it should be sufficiently small. Why? For some reason we'll see, but it shouldn't be too small either. So there's like a trade-off. This should be sufficiently small for analytical reasons, for proving things and all that, right? but I cannot take this to be h, right? This h, necessarily this h is positive. In fact, I would try to make h as large and just to be more aggressive, because this gives you measures the progress, how much you're moving. I wish that h is as large as possible. So you see, there's a trade-off. You cannot make it too large, right? Things might break down, and you want to make too small. Because why? Because it might stall, right? It might move very, very slowly. Then in that case, right? So, question is your factor. The thing is factor on the choice of an age. Provided if you don't pick age correctly, it might not work. But let's say you picked age correctly and everything is done. Let's say for a convex differentiable optimization like this, where there are no constraints, can you say that xk converges, right? But you see, we are not primarily interested in this question, right? We don't care about xk's. You see, xk is in some sense an artifact of your algorithm. It's not part of your intrinsic definition, right? When you're trying to compute this f star, there's no xk here. So this is an artifact of your algorithm. Because you decided to solve it iteratively and that using gradient descent, this is something that came out of that. And you're trying to basically say that, okay, look, I mean, the algorithm is stabilizing and all that, nothing bad is how it's not diverging, for example, or it's not oscillating. But you see, that's not what I care about. I care about, can I get this value f star or not, right? Using this algorithm. Fine? So you see, at a very high level, you must have actually a guarantee that the problem is nice. So for example, this cannot be minus infinity, that this is a finite number, right? So you see, if you start with a problem which is hopeless in itself, then there is absolutely no algorithm that can work for it, because it doesn't have a solution, right, in some sense. So at a very high level, there are certain things that you have to fix for the problem itself. So a very standard assumption is problem is solvable. This is a very standard assumption. That means f star exists, and in fact you can find an x star. This is equal to some x star. So this is the solvability. The problem is solvable. There's a basic assumption that you make. In front of this, existence of this x star is super critical when it comes to analyzing the algorithms. You will see that I'll always try to compare this guy. So it's like might not be able to show that xk goes and hits one of these x stars, because you see, there can be many x stars like this. I didn't say it's a unique minimizer. There can be many x stars like this. What does this mean? To be very pedantic, this means that there is a set of solutions and this is just one of them, right? Point is, some of the analysts that we see is typically we try to compare this xk with one of this x star, right? So the existence of the x star will be very critical to the proofs, but what we care about is the following. I have to erase, or maybe just erase this question. This is the big question. I set out to compute f star. I chose a iterative method which generated certain iterations. These are called iterates, this xk's. And I want to understand that the objective, f is called the objective function, right? So f evaluated at those guys, these are kind of approximations of x star, and I hope the approximation gets better. In the limit, asymptotically, do I hit f star or not? So that actually is my core question. Right? Now, notice something interesting. If f is continuous, if f is a continuous function, which happens to be the case, you know that for example, if you look at this setting, and see Rn, and if you have convex function on all of Rn, then it is necessarily continuous, right? You remember this fact, right? On the whole domain on R or Rn, if you have a convex function, of course, assume that domain is the full set, then the function is necessarily continuous. In fact, the domain is open, then the function is continuous on that open set. Now, so So you see, one interesting thing is this it's tempting to kind of say that, oh look, let us make this mild assumption that f is convex, then if I can show xk converges to x star, again, x star is one of the minimizers, then by continuity I get that fx should go to f star, right? Because fx should go to f of x star because xk goes to x star. So if by continuity fx should go to f star, which is what I want, right? That seems a very, sort of a very natural strategy to take. Turns out, as we'll see, excepting for very special cases like strong convexity, when you have strong convexity, answering this question is very, very difficult. In fact, it's for almost standard most analysis and the kind of assumptions, this we cannot answer this question, whether xk goes to x star or not, right? We can only answer this question whether this is called objective convergence. Does the objective converge to f star or not? This is called domain or iterate convergence. That turns out to be a very difficult thing to say unless you have some technical things like strong convexity. But objective convergence is already quite challenging, we'll see. Telling that the objectives converge is already quite challenging. Okay, so I'll try to highlight these difficulties rather. The proofs are already worked out. I believe there are not one or two proofs missing which I'll cover. I think projected gradient descent, you will see. Somewhat I've given a statement without proof. I'll cover that. And they're quite technical. There are many parts to that. That's why precisely I gave you an assignment, PS6. There's noise. There's a lot of technical things which are important, but they are technical nonetheless, and they kind of block the main idea. So I've tried to separate out at least for some examples. So these are very technical things. You don't know why you do them. I can give you intuitions as to why you do rather. It's not I take but my statement. There is an intuition or understanding on why you want that inequality. That's clear. For example, if you want to control the function using the gradient or the vice versa or something like that because you want to, I'll give you those intuitions, but the way you get those inequalities sometimes are a little mechanical. They do come from some geometric intuition about this majorizing, sort of this subgradient constraints and all that. But the way you do is a little mechanical. Right? And so, for example, you might forget it if you've not done it for some time. But at a high level, you should understand what inequality is being used, or rather, qualitatively, what are we trying to control using? What is leading to what? The causality. Those little lemmas, the proofs, how you prove them, it's natural to forget, and given some time, you can model them out possibly. But at a high level, you can understand questions like this. What can at all be done? You come up with a research problem, and you're trying to solve that. You should know that these are the limitations. This is what you can do, and this is what you cannot do, unless you have more structure on the problem. So rather understanding that, I've tried to sort of emphasize them in the notes, but while during the lectures, I'll try to focus on them. Okay. So just to let you know, please, just to remind you, please look at the notes. Right. This is like a very short summary of a lot of things I've said in the first couple of pages. That there are questions about solvability of the problem, existence of minimizers. That means then there's things about convergence, objective convergence, iterate convergence, and all that. Just one thing I would just like to add here is, oftentimes we are interested, especially in engineering applications, or let's say so-called practical applications where you want to code it. Let's say, so if you do not have a concept of a computer, this is good enough, and mathematically this is good enough. Let's say, well, it converges, but so to say, it's a zeroth level question you can ask about convergence. But you see, if you're doing that on a computer, the very second thing you ask is, in fact, you ask two things, right? How efficiently can you do that? How fast can you get from here to here? Let's say if there's a fixed cost, right? You have to compute the gradient every step, which is not cheap. For example, like if you've done machine learning, computing gradient can take a hell of a lot of time, because this can be a composite you can this be a sum of terms over all your data and then you have to add them up and all. This can take a lot of time. So every iteration, every update can take significant amount of time. So you wish to know how fast can I get there? In 10 iterations, 5,000, how many iterations should I get? Now, turns out these are very difficult questions that are very, they're not very satisfactory answers to that. If you have to do that mathematically, the only thing that people do is talk about rates, frankly. This is I would call what is called mathematical rates rather, rates of convergence. And there's a difference between mathematical convergence, what this means mathematically, and what the computer does, which is like empirical convergence. There is a little disconnect between the two. They are correlated in some sense. So things which are fast on pen and paper turn out to be often fast when you program them well. So there's notion about how you program and all that, right? There's a lot of mess there. But let us say this is the zeroth order question. The first order question is, what is the rate at which, how fast are you going? So that necessarily subsumes so when you say rate, it's understood it converges, necessarily converge, how fast. So some of you have studied CMO and all that, would know that there's notions like sublinear convergence, right? Then there's quadratic, exponential, right? Convergence and all that, right? So exponential also what is called linear convergence. That's why it's called sublinear, right? So then Newton's method, most of you have studied Newton's method, right? So what happens in Newton's method, if you look at the error, in fact the error not in this, but in the error in the discrepancy in the iterates, okay, is the difference between this and one of the solutions, or either the root, because Newton's method is finding roots. That what happens is, if you typically do that on a computer, you'll see something interesting. Up to some steady state, like first few iterations, if you look at the error, that means xk minus x star, the number of zeros typically tend to double. So you have 1 0, then 2 0, 4 0. As I'm saying, roughly, you see that pattern of zeros. There is a theory that tells you why that happens. Locally, you can prove convergence actually. In fact, for Convex, you can prove globally also. But let's say Newton's method is known to converge quadratically. What does quadratically mean? The error at some point is square of the previous error up to some scaling. So that's what is happening. If you look at the error, then you had 10 to the minus 2, it will become 10 to the minus 4, then it will become 10 to the minus 8. What happens with gradient descent? It's worth checking. Try running gradient descent. It's like what is called sublinear convergence. Like it can be 0.000 and it's just one decimal place for 20, 30 iterations. And then maybe after 100 iterations, 2 decimal places. After 150, maybe 3 decimal places. Newton's method is like it's doubling every iteration, right? There's a price, there's a cost, right? You pay additional cost. It's not that simple. You have to actually normalize it by the Asian, right? Okay, so having said that, it's kind of a very, let's say, a vague introduction to the topic. I really suggest that you look at the notes which I've written it very, I've taken time to sit and think about all the points and jot them down. When you do it on a board, you're typically doing some kind of random access somewhere and you find some information. So this is a we look at gradient, a lot of variants of that gradient descent and quite a few things. I'll jot them out right now. So I'll tell you exactly what topics or algorithms we will cover. I had a comment to make, rather a remark. Remark is that, so as I said, there will be 3 lectures, and the whole idea is to watch the lectures before I start doing the online sessions on Teams, right? I'll use Microsoft Teams, I'll send out an invite next week. So it's understood, even I'm okay to give a little more gap, but you see I need typically 3 to 4 hours of this video lectures, and where I describe the main ideas, the algorithms, and the results, the convergence results, because understanding the results is something. The proofs, mainly the proofs would be done during the online session because I have to work them out and I have to tell you certain things also, why certain, which is not there in the notes. It's like mechanically, you do this, so I have commentaries to that. What is important is you will be lost if you're not seeing the video lectures before attending that. Second is I want to keep the questions to minimum because I would already be discussing something to the Zoom lectures. I would typically ask you to keep the mics mute and all that. And I might have actually separate Q&A sessions where uh, maybe one Q&A after this immediately and one or couple of more Q&A after I do the proofs. Okay. Now, as you understand, because I've worked out the proofs, I will not write out everything. I'll only give the sketch, the main ideas of the proofs. You can find the nitty gritties in the notes. Everything is done like I've checked and rechecked, everything is correct. As I'm saying, there's one proof missing which is not even documented there. The proof is stated, but the theorem is stated, the proof is not done. That I will do, that will spend some time, it will take an hour literally. But apart from that, I'll be giving only the sketch of the proof. So what does that mean? It means that you are expected also to look at the proofs on the notes and try to understand them a little in tandem with the sort of the kind of explanations that I offer during the lectures. Okay, so I was about to ask you if you have any questions or not. I realize I'm talking to a computer. Okay, so yes, so let me see how long are we into the lecture, 36 minutes. Yeah, let me spend some time discussing unfortunately I don't have the notes with me, I dropped it at, the syllabus is, I don't have the syllabus, but I do remember what's there in the lectures. Just wipe this off. Okay. So let us look at what's there. I mean, what topics or algorithms we'll be looking at. So first, so the list of, let's say, I'll do it this way, sorry. I'll write the model. By model, I mean the optimization problem, the model of the problem, abstractly what it is. See, the whole purpose of setting up this segmentation is that you can actually switch. So not switch really. So for a given model, there are many algorithms to solve, and a given algorithm can actually be used for different models. But yeah, so I just want to emphasize that. But basically few models here, and the kind of very basic models that you have already might have seen. So one is something like minimize fx unconstrained optimization. Maybe it would help if I pull it up a little. I think you can switch. No, it's worse. This is better. Okay, so this if differentiable on Rn. Mind you, this is just what you barely need. These are the properties that you barely need to set up the algorithm. There's a difference here, very subtle. And remember this point I'm telling you. This is the barely the information that you need to even define the algorithm. As is usually the case, to prove things, you need a little more than that. You need a little more structure. So, for example, I'll tell you what this means precisely in this case. So here what you have is model is gradient descent. Let's say the algorithm is gradient descent. Xk plus 1 equals xk minus h drag. I'm just writing the update. Right? So you need to define the gradient, which is the bunch of partial derivatives. And well, I mean, you don't need differentiability as such. You can have just the partial derivatives. That's good enough to do this. But it turns out, eventually, you need what is called C1, that the derivatives exist and is continuous, or at least the gradient exists and is continuous. That's what you need. So what is called this so-called Lipschitz continuity. So you need something more, one more bullet here. It's like the gradient is not just continuous, not just uniformly continuous, it's Lipschitz continuous. This is much stronger. Lipschitz continuity is stronger than uniform continuity, and uniform continuity is stronger, of course, tautologically than continuity, right? So yeah. So the bottom line is that you need a little more. So I'm not getting into those details. Those would come up when you look at the proofs of the theorem, the statement of the theorems, right? Which I do as and when the topic comes up. I'm just describing. Okay. Then what we have is so I'm not repeating that C is convex and all that. C is closed. Well, why? You will see that I need to define a projection. Of course, C is convex. That's given already, and if it is convex, I'm not writing that. But C is closed. It has to be a closed set because it's so that you can define projections, right? And I write it here. So I put it in brackets because this is a consideration that comes up when you're actually trying to implement things and all that. But fundamentally, the algorithm is defined as soon as these two conditions are met. But I mean, this is something we put a star here rather, that the projection. So you can have closed convex sets which are very complicated. So I'll give a simple example rather, not very. So you know what is a simplex is, right? The simplex is a structure that comes up in linear programming, for example. So just for simplicity, like think of polytopes, right, or polyhedras, right, bounded polyhedras. It turns out that that's of course a closed convex set, right? It's the intersection of half spaces which are closed. So what happens is it turns out that it's not easy. This is not easy to compute. It's computable in a certain sense, but you don't have closed form expressions, and sometimes you remember projecting is an optimization problem in itself. You have to argmax or like the point which is closest. By definition, it's an optimization problem. So this might have to be computed iteratively, right? But it can be done for simplexes. There are bodies for which it's not known how to compute the projection fast. But keep this in mind. So what we can is for GB. There's something called PGM that will come up later. Don't confuse it with this. Is projected gradient. This is PGD for short. So what this is, it looks exactly the same. So you do what you do in gradient descent, right? But you know that you don't have a free play. You have to find a minimizer in C. So what you do is heuristically, every time you move out of the region, you try to project back and then try to get to a point which is closest to C because you want a point from C, right? So just think about it. A pretty simple minded solution could have been like this: you run gradient descent till convergence. Let's say you found X star, and then you project exactly, let's say, and then project X star into this C. You can pretty quickly argue that that would not give you a minimum of this problem. What happens is when you run gradient descent, you didn't take this into consideration, right? When you solve for the minimizer of just F on whole of Rn, right? So if you project, then it's you can clearly cook up examples where the projection of the minimum extra on C is not the minimum of this entire thing, right? Because when you computed that X star, you didn't take into consideration this C, right? And just moving to a point closest won't give you the optimum solution. Rather, this looks like a reasonable way, but you still have to show that this works, and we will show this works. So what you do is you take a gradient. This is called a gradient step, and then you project. Right? So not very important, but you see sometimes what people do is right is that or rather I'll skip what I'm trying to say, but we'll see that there's a structure with the way I've developed some of these things. There's actually a hierarchy. So for example, you can clearly see that this reduces to a gradient descent when C is Rn, is the whole domain. Then projection is trivially the identity operator. There's nothing to do. Projection of X is X. So this reduces to gradient descent, right? We'll continue with this hierarchy. So we'll look at, we have about 12 minutes, we'll look at more sophistications of that. So for example, we'll see that this idea of projection, taking projection, can be generalized using what is called proximal maps, right? We'll see that shortly. And there's something called proximal gradient method, PGM, right, that comes up. Okay, just to be, I'll come to that shortly, but it turns out there's a little different route that can be taken from here, which is not this straight hierarchy, is something lateral, which I wish to talk about because it's very relevant for current optimization, is stochastic gradient descent, SGD. That's kind of an outlier. It doesn't sit in this really hierarchy, the one I'm following, but I'll just briefly mention about SGD. So erase this. I'll just erase this one, and so you have the same model in SGD, but the setting typically is this. You have, let's say, f of x, right, which itself is so you have a law. I mean, the typical setting is a machine learning. You have loss, which is actually the sum of elementary losses, and this I corresponds to a data. So in fact, you have the same f loss evaluated on different data, but abstractly I can write it as different loss functions, right? Because your data is changing, and these are convex functions. This sum of convex functions, right? Differentiable functions. So this is the setting where you can have constraints, but let's look at the vanilla example where and of course convex. Okay. Now you see, nothing stops you from doing this. So you can take the gradient descent, which is sum of the gradients by linearity of gradients, and then you can very well proceed with gradient descent. The point is that computing the gradient is you will require to compute m, and then can be like number of data points, right, which can run into at least thousands or even millions, right? So this is challenging to compute, even like what is called a first order method, where you're just working with the function and the gradient. Gradient descent is difficult. So what people do is they use what is called for this model. So M, like this is the idea is that M is large. If M is small, I would not bother to do this. So what you do is, right? It's called SGD, stochastic gradient descent. What is stochastic about it? Why do you want to do stochastic? I mean, you see, there's a non-stochastic gradient descent you can think about. Very simple-minded idea is that, well, I mean, it's a sum of many things, and first thing that comes to mind is, well, I mean, let's just pick one, right? Let's pick one data. It comes from an intuitive idea of learning, right? So just pick a data, see, assess the loss on that, use that to update your parameters, right? This X would be your parameters, the machine learning parameters that you have. It could be the weights in neural nets. So you use that to update this, right? See, what happens is, well, you can do anything under the sun, right? You can come up with your own heuristics, but you still have to prove that certain things work, right? So with SGD, the way you do it in a little more disciplined way. What's the and what exactly is that? Uh, is you sample from your data points typically. You uniformly sample from 1 to m. That means you uniformly sample your data points. You pick one guy. You look at its gradient, right? And you just use that. So basically, the step would be like this. So as I said, what is y? Well, I mean, y depends on the iteration. So y is one of these m's which have been randomly sampled at that iteration, right? So if you're doing it randomly, you're hoping that you'll be able to see all the data points and all that, right? So that would be your that is your SGD. The reason I wrote this as f, there is a reason for that. I could have just written it sum of fi's. The reason I wrote it as f is because you can abstract it out. Right? You can also do SGD when it's not like this, when it's general F. You can also do in this setting SGD. Turns out that abstraction helps in the analysis also. What is that abstraction? Abstraction of this. So what I get something which reduces to this, but it's a little abstract. So this is the let's say the vanilla version, and the abstract version is like this. But you can also do projected SGD. That means you do this and you project. Also, all kinds of soup you can make. I'm very sorry. I forgot the index A there. Yeah. Okay. So this is that simple abstraction that you can do. At every step, right? You move not opposite to the gradient at that point, but along some direction. This is random, right? So this is a random vector in Rn whose expected value is the gradient at that point xk. So that's the thing. So you're not doing exactly grad xk, but you're doing something which is fluctuating, but its baseline, the mean is grad of xk. So it will be plus minus, I mean, loosely speaking, this is gradient, this mean, plus minus some noise. That's coming from the sampling process. So this is the abstract setup for gradient SGD. How do the two relate to each other? You see, just think about it. What you're doing here is you're picking just one eye, right? So if you define this random vectors vk using this process, that means at a given iteration k, you randomly sample from 1 to n, right? You pick I from 1 to m and you evaluate the gradient at that point. you can check that the expected value of Vk would actually be the gradient of fxk, right? Why? Because you see, um, you're sampling uniformly, right? So it's like, I mean, so that's precisely the reason why, I mean, in optimization, this factor doesn't matter. But it's written like this precisely because this, if you take the expected value, you get this. When you sum this up, this is the average. So if you take expectation y equal to 1 to m, right? You're taking one of them, so it's probability 1 by m, and for a given choice, the gradient is grad of fi, right? So in that case, what you have is gradient of the random variable is precisely the expected value of the random variable is precisely the gradient at that point. Okay, so in fact, this is equal to right. Vk is one of these gradient values which you have sampled for that, right? And this is your average over the uniform distribution, which is precisely the definition of expected value of Vk at that point. That's equal to this, right? So this is by linearity. So this is by linearity of gradient, right? And this one, rather, the ones that I should have switched there, that's the definition of expectation, right? You sample it according to the process that I just mentioned to you, right? So this is the model that instead of writing out every time gradient of this and all that, so this is the model that we'll use, like you're moving along a direction and on an average you're supposed to move inverse of the gradient. So this is the model that we use for analyzing stochastic gradient. And of course, the advantage is that you need not be a sum of objectives. You can generally have any function for which sort of computing a true gradient is difficult, but you might have a noisy process of let's say a noisy approximation of the gradient, and if you can show that it's unbiased, right? So this is unbiased. All the gradient estimates are unbiased. Then you can show actually gradient works. As you know that it's a stochastic process, you can't make deterministic statements. So for example, fxk cannot go to f star. We show that it goes to f star in expectation. And there's a catch there. There's a small, because of the noise in the process, there will be a small bias term out. So if you look at the statement of the theorem and also look at the proof when we do it, it will be clear. There will be some small noise term coming in because of the sampling process. That's a penalty. So that's a penalty of paying for the sampling, and your suboptimality is coming because you're doing it iteratively, right? So for gradient descent, that noise because of sampling is not there. In this case, there will be a noise. Okay. Let me see. I don't wish to make the lecture very long. So yeah, it's almost 1 hour. So let me just stop here. So we spoke about gradient descent, projected gradient descent, and stochastic. In fact, those are pretty much the 3 type of gradient descent. We'll analyze. We'll rather look at the sketch of proofs. Well, if it's short, we can look at the proof also. But the important point is next lecture, we'll be discussing something very interesting, was called proximal gradient method and ADMM. So you see, in all of these cases, it's a little weird. Like every time it's like gradient. What if f is not differentiable, right? So it turns out those are the 2 things you can do. In one case, actually, you do assume that at least something is differentiable, and in the other, you actually assume that everything is non-differentiable, and you still hope to find the minimum. That's called this alternating direction method of multiplies, ADMM. But just before I end, let me write down what those 2 things do. It's precisely, the model here is for rather is what is called a composite optimization. plus g, you want to minimize f plus g, you can assume both are non-differentiable. The interesting thing is, again, this subsumes almost everything that's kind of interesting in the first order method. In fact, as far as applications are concerned, this is good enough to cover, well, I mean, in some sense, at least if you look at areas like computer vision, image processing, computational imaging, machine learning, just name it, statistics, almost 99% problems come under this framework. In fact, you can show that any, you can show any problem, including the constant optimization problem, can be written in this form f plus g. Yeah. So, and f need not be differentiable, so it actually covers everything in some sense. So it covers all the models that, I mean, we spoke about just now. The important point is fg are of course convex. Of course. But there's a small catch. G can be what is called extended real value, that this can take infinite values, which is of course just a nomenclature, it's a definition. But I'll come to that. G can be, I'll come to that next day, can be extended real value. It's allowed to take plus infinity. Why? Precisely because we'll see can it reduces to other models in that case. But importantly, there is something called proximal gradient. This has many names. It's also called FBS. Forward backward splitting. In imaging community it's called ISTA. What happens is people discover, rediscover, and then they give their own favorite names. So these are in optimization community, these are the standard names, and this is even more standard proximal method in some sense. Boyd has a nice tutorial on this proximal method actually. It's not a book, but it's a very, yeah. So there's a journal called Foundations and Trends in Machine Learning or something. So it's a very nice tutorial on that. And then there is ADM. I don't have time to write. I mean, this is called, I'll write next. It's a long thing. It's a mouthful. Alternating direction method of multipliers. I mean, just call it ADMM. Yeah. So we'll see that here. Both FG can be non-differentiable actually, but in this, so in this case, typically what happens is you assume this is that's why you write separately, otherwise you could have combined them. This is smooth, what is called smooth. It's differentiable, whatever, first gradient, Lipschitz, whatever you want. This is nice, this is bad. Bad in the sense that it's convex, but it's not differentiable. For example, this can, for example, be an indicator function of some set. That's why we need this plus infinity, or it could be some other discontinuous function as well. For example, this can be what is called the L1 norm, right? We've seen that not all functions, continuous functions are differentiable, right? So, for example, this can be the L1 norm, and that's why in image processing and other fields, this L1 minimization, there's a big story I'm not getting into, the sparse signal processing. So, this fact that this is L2 and this is L1, both, if you add them, they're convex, but you can exploit the structure individually, that this is smooth L2 square, the loss is smooth, and this is called a regularizer for machine learning and imaging. That the regularizer can be bad, non-smooth, but this is typically loss can be smooth most of the time. This can be exploited in forward proximal methods and all that, right? So they can, if both are not smooth, you can have examples, then you can still solve it using what is called ADMM, provided you can compute what is called a proximal map. I'll come to that later on, but that is all about this this topic on algorithms, right? So we'll slowly go through all of this. I give you the motivation next day. I hope to bring my notes. I may have missed something. So yeah, so by next day we have covered all the algorithms and yeah. So if there's some yeah, so we'll see if I'm done by next day. Then maybe I'll take a break. I mean, small pause, and maybe I'll start doing the Zoom lecturing from let's say next week. I'm waiting for Chidai to actually be done with this part. Okay. Yeah, so there's no scope for questions here, sorry about that. And please note down your questions and be precise when I'll ask you to actually mail me your questions after I'll compile them and then discuss in the class. That's the way I plan to do. You can't be, I mean, it'll be a chaos if I allow you to shoot questions, so you have to document your questions, having watched these lectures, and then you have to get back to me by mail and compile them, and if required, anonymously compile them and distribute to the class and so that that's a basis for the discussion. This is the algorithm that I have in mind. Okay, okay, so with that I'll stop here. I'll log off and take care. So see you next day.